Okay, so in this first lesson, I'm going to give you an overview of what's known as the tangent line problem in calculus, and I'm kind of going to just touch on what the real applications of calculus is, like why was calculus even, invented? Like, well, what was the point of it? So then, the first thing we're going to go over, and we need to make sure that we understand what a tangent line is. So a tangent line is a line that only touches a curve at one point. So it could look something like this. Let's say I have a curve, maybe that goes like that. And there's this point right here, and a tangent line would be something like a line that does this. I don't like the way that T looks. Let me fix that. Now the first chapter and part of the second chapter actually deal a lot with this concept of a tangent line. And the reason for that is because a tangent line of a function lets you understand how the function is changing. So if we can understand how the function is changing, then we can understand the function and kind of predict what's going to happen down the road. So let's draw an example of some common functions that are used. So let's have our y and x axes. Now let's say we're trying to figure out how far you're going to travel while you're driving your car. Now in algebra and pre-cal, up to now, you've pretty much just learned, okay, well, distance is is speed times time. So like if you're traveling 50 miles an hour for 3 hours, you're going to be 150 miles an hour. So graphically, you would have a line that looks like horizontal, where this is equal to y is equal to some constant. So let's have your y-axis again represents your speed, and physics we call it also velocity, and x is the time. And that's how we get distance equals speed times time. But as you probably understand, in real life, your speed is not going to stay the same. When you're driving on the freeway or you're driving anywhere, driving to the store, you start at 0, you accelerate to some speed, and you have to stop because of traffic lights or traffic, and there are some points you can speed up. So your speed is not, it's not going to be simply at the same rate the whole time. It may look something like this. It may, it starts like this. You have to then slow down, and then, you speed up again, and then maybe you have to stop, and then you speed up again, and so forth. So here's an example of, of a real, like, this life situation when you're driving a car. Now, if you're going to figure out how far you traveled based on this function, it's not just going to be like distance equals speed times time, because your speed is changing. Your speed is represented by this curve that's going up then down, then increasing and decreasing, that sort of thing. So the purpose of calculus is to be able to figure out and understand behavior like this. And we're going to be dealing with this sort of thing throughout the course. But first, let's get the idea of what a tangent line and how that works in regards to rate of change of a graph. So let's look at this first problem. Okay, so here let's say we have this tangent line to the parabola at the point 1, 1, and we want to find the equation. Now keep in mind that we're given this tangent line. Typically, you're just going to be told this, this is your problem. You're not going to be shown a picture. So if you want to find the equation of this tangent line, since we know it's going to be a linear equation, it's going to have the form y equals mx plus b. Now we have to find the slope in the y-intercept. That's our common, technique. We know that slope is, typically you'll learn it as, y2 minus y1 over x2 minus x1. So we want to find out the slope first of this line. But to find the slope of this line, is going to be, impossible using this because we're only given one point that it goes through. how are we going to find the slope? We were only given the coordinates of 1 point. And again, let's pretend that, you don't know that it goes through this point or any other point that you can see on the graph, because, you're not going to be given a picture of the graph at all. So you're not even going to really know how to draw the tangent line. This is just given to make it easier for you to understand the idea here. Now, so since we can't find the slope straight from this line, what we're going to do is create another line that has a slope similar to it. And those are going to be known as our secant lines. So a secant line, remember, is a line that goes through 2 points on a curve. So we could draw a secant line that goes, let's say through here and here, through a point here and the point 1, 1. And this would be an example of a secant line. So we have a point there. And then if we can find the slope of the secant line, that's going to give me an idea of the slope of the tangent line. So the goal is the slope of secant. What's the slope of the secant line? Now we use it. Now based on this secant line, we can actually pick points specifically on the parabola. 1, 1, and maybe in this case it'd be like something like close to 1.5 and like 3 or something like that. So that's the idea. But if this slope is not exactly the same as this one, so what can we do to improve our estimate? Well, you can make another secant line whose points are closer to this one. Maybe we can make a secant line who goes through a point here and here, point P, and a purple line there. It's another secant line. And the slopes, would be much closer to the slope of the tangent line, as you can just see by looking at it. And the idea is keep on applying this strategy. We take another point, like super close to the point P, and make it so that its slope is going to be nearly the same as in the slope of the tangent line. So the big idea is to find the secant line who goes through points on the function with points, let's say, points on the function. So put points on the function f of x, but also where the points are basically, we say, infinitely close to point P. Close to P. Now, this idea of infinitely close, we're going to learn in this chapter that it's known as a limit. So let's go through some actual examples where we apply this so we can really understand how the mathematics work. Okay, so what we're going to do is we're going to find the slope of the secant line of not just one, but various secant lines that go through the point P that we found earlier, 1, 1, and through the point that will be determined by the given x value. So for example, if we're looking at the secant line that goes through the line x is 2 and point P, so P, remember it's at 1, 1, and x equals 2 would be at 2, 4. We're going to call that point A. Let's draw this first one in pink. So let's first review, how slope is determined. So again, the basic, equation you learned for slope. is usually, something like slope is equal to y2 minus y1 over x2 minus x1, where, the points are at x1, y1, and x2, y2. Now, in this case, we're going to leave P as always going to be our x1 and y1, since it's always going to go through P. Now, for this first example, x2 would be, 2, and y2 would be 4. Now, since we're trying to figure out the values that, lie on this function, y equals x squared, we would also look at this as the slope being equal to f of x2, because the y value we get for y2 is when we plug in x2 into there. This one is pretty simple because when you plug in 2 into x squared, right away it's 4, so 2, 4. But we can represent this as also being f of x2. And this could be, x2. So let's write this as x2 and f of x2. Now, our x1, we're always going to be looking for the slope of the secant line that goes through this point. So x1 is always going to be 1. And then y1, again, will be calculated by f of x1. Or instead of writing, instead of writing f of x1, we just write f of 1. Let's go a little further. F of x2, since we're dealing with the equation y equals x squared, f of x2 is, x2 squared. So we're taking whatever that value is, x2 squared. And from that, we're subtracting f of x1. And f of x1 is always going to be 1. And same thing with y1. So we can write that as x2 minus 1. So that's just a simple way to, kind of keep in mind. Anyways, so let's look at the slope of this secant line. So this is our first secant line. So let's write this secant. Secant line A, let's call it PA actually, PA. And its slope, we're going to make it equal to, the difference from here to here. We can see it's, it's going to be 3 over 1, but we'll make it again. Remember, f of x2, 4 minus 1 over 1 minus 1. Or sorry, no, over 2 minus 1. And we'll get that it's 3 for that first one. Look at the next one. Let's say if it goes through 1.5, so 1.5 will be something like over here. So we'll call that point B. And B is at 1.5, comma 1.5 squared, since we're talking about the line on the parabola, and 1.5 squared just happens to be 2.25. And so for this, we can write the slope of the secant line and we'll call it PB. Will be 2.25 minus 1 over 1.5 minus 1. We'll get that it'll be 2.5. This notation's not important, just whatever works best for you. Let's keep on going now. Let's look at the slope of the secant line that goes through the point 1.1. So 1.1 will maybe be something like this. Can't really even see it any further. So 1.1, that'll be C. And that y value, 1.1 squared, you'll get 1.21. And so the slope of this secant line, PC will be 1.21 minus 1 over 1.1 minus 1. And we'll get 2.1. Let's go through two more. Getting closer to 1, so 1.01. So basically, you can't really even see where it is. We'll say that's point D right there. I mean 1.01 and 1.01 squared, which will be 1.0201. And so then this slope will be slope of PD will be the 1.0201, 0.0201 minus the 1 again, over the 1.01 minus 1, and that will simplify to 2.01. And we'll do one more. Through x is 1.001. And let me write this down here. So point E, 1.001, comma 1.001 squared. You'll get 1.002001. And then so the slope of this secant line will be equal to 1.002001 minus 1 over 1.001 minus 1, and you'll get 2.001. So you can probably see the pattern that's going on. It's just slopes are getting smaller and smaller, and it seems that they're getting very, very close to 2 as we get very, very close to x equals 1. Now, we're approaching it, from one side, but what would happen if we approach it from the other side, from the left side? So let's say that we're now going to look at the slopes of the secant lines. We're still going to go through our point 1,1. But we're going to look at points that approach from the left side. So let's say x equals 0 is our first one. So we would have our point F at 0, 0. So our secant line would do this. So the slope of this secant line, called again PF, you would still go ahead and can do 0 minus 1, remember, at y2 minus y1 over x2 minus x1 over 0 minus 1. And you would get 1 for this first case. Now I'm going to go through the rest of these a little bit faster, just since we probably got the idea down. So this will save you some time. But if you're good with this, you can feel free to jump ahead into the end part of the video. So here we're going through the point x is 0.5, which will be like this. So we'll have our point at 0.5 and 0.5 squared, which should be 0.25, be point, again, we'll call that point G. So the slope of the secant GP will be 0.25 minus 1 over 0.5 minus 1. And here we would get 1.5. H, we're at 0.9, so we're getting a lot closer. So H would be at 0.9, and then for Y, we have 0.9 squared, so 0.81. And then so the slope of this line, HP, we would get 0.25 minus 1. No, sorry, 0.81 minus 1 over 0.9 minus 1. And we would get 1.9. Now for point I, we're at 0.99. Point I is pretty much on the graph here. So at I would be 0.99, and 0.99 squared would be 0.9801. So the slope of the secant line through IP would be 0.9801 minus 1 over 0.99 minus 1, and we would get 1.99. And our last one at 0.9999, 0.999 actually. So let's go ahead, let's just move that like J, so we can write it out clear, the 0.999. The Y value, 0.999 squared, we would get 0.998001. And so the slope of this secant line would be 0.998001 minus 1 over 0.999 minus 1, and we end up getting 1.999. So you can see that these values are actually increasing and I'm getting very, very close to 2. They're getting super, super close to 2 as X value gets very, very close to 2. So now let's put it all together in a table. And so if we put all these values in this table here, we can see as that we're approaching the point when we first did it from the left, so coming from this direction, or sorry, from the right, coming from this direction, we were decreasing. And when we were approaching from the left, in the second part, we were increasing. And so you could probably see and guess like the slope there is going to be 2. And so what we say is that as this point, or as a point on the function, in this case y equals x squared, gets closer to that 0.11, the slopes of the secant lines approach the slope of the tangent line. And we talk about this in the sense of a limit, which again we're going to go into in this chapter. And we say that it's going to be the limit of the slopes of the secant line.